Welcome everybody. Special seminar. It's very, we're really honoured to have a very special seminar, I should say. We advertised it as a seminar and it's become an evening with Guido Imbens. We're really honoured to have the Nobel Prize winner, Guido Imbens, from Stanford here. It's wonderful to welcome Guido back to UCL. In fact, I think back to this very room where you were speaking at the World Congress, I believe. Guido's been a good friend to the department and has visited on many occasions over the years. And I think the first time might have been around the time you were doing your Masters in Hull, in the UK. And certainly very soon after that. And of course way back in the last century. Of the many talks I particularly remember is the brilliant talk at the Econometric Society, as I said, I think was here, which we held in 2005, and that was on non-additive models with endogenous regressors, something that stayed very close to the hearts of many of us in our work. As we could see from the huge demand for meetings with Guido today, he's always an engaging and inspiring person to have around. Not only thinking of great new ideas and ideas that help push forward the field of econometrics, but in a way that's extremely, enormously helpful for empirical researchers. In fact, I see that his title is the Applied Econometrics Professor at Stanford. The paper, of course, with Josh Anger's 1994 on local average treatment effects is the case in point. It's hard not to go to any applied seminar where that work is not referenced and, of course, highlighted in the Nobel Prize citation. But there's much, much more, of course, to Guido's work. Extensive work on evaluation methods and causal inference, major advances in instrumental variables, propensity score methods, matching methods, differences, regression, discontinuity. I could go on, a huge number of leading publications, and I know the students here are kind of gradually wading through Guido's work. And it reaches way beyond applications in economics. There's applications right across social science and now in biomedicine of a lot of the developments that Guido's been behind. And alongside each of the development is always an important application. It's got applications to education policy, health policy, social networks, labour supply, training. I was kind of running through the list. It's really a remarkable contribution. And it's been noticed by many of us, and of course in particular by the 2021 Nobel Prize Committee, as they state, for methodological contributions to the analysis of causal relationships, noting that many of the big questions in social science deal with cause and effect. Some of these questions are possible to answer using natural experiments, and then they go on to, of course, point to Guido's work with Josh Anger's. And it kind of seems natural, if you think of this work, that it would lead Guido to think about how best to combine experiments and observational studies, which is, of course, the focus of the talk today, using experiments to correct the selection in observational studies. So I know we're in for a treat, and I'll hand over to Guido. As I do that, I think it's a big lecture theatre. In our normal seminar, we have a lot of interactions. I think you can feel free to do that, but maybe it's best to leave questions for the end. We've got plenty of time for that. And so reserve big questions for the end and think of some as you're going along, and we should have plenty of time for interaction after the talk. So let's welcome Guido Imbens to UCL, please.
So I think the first time I visited the UCL was in 1985 or 86 when I was doing my master's in Hull. So I was very appreciative of the invitation for which to come here, and I've been back many times since, including at the World Congress in 2005 5, as Richard mentioned. I haven't been back much in recent years. I think actually this is the first time since Brexit and the pandemic, the world has changed. It's with great pleasure that I'm back here. It's very nice to be in this room. I don't actually remember being in this lecture room before for the World Congress. If I'd known they had the table here, I would have brought my the t-shirt from my Berkeley years, where we were not quite so proud of the inert gases, but we were much proud of Berkeleyan, Californian, and Lawrencian t-shirts with those 3 elements on there. But so it's great to be here. I want to talk about some econometrics. I was somewhat taken aback by Richard's comments that the students here are wading through these papers. I hope they were skipping through them rather than having to wade through them. So here's some work. As you said, this is. I'm actually going to talk about parts of 2 papers. Both of them I joined with Susan Athey and Raj Chetty, and actually one of them is also joined with Hyunsuk Khan. And they're kind of part of a kind of bigger project, so at least a lot of time we spent thinking about how to combine observational and experimental data. And so Susan, Raj, and I came at these questions kind of from different perspectives. Raj had been involved in some experiments, but also was kind of doing lots of studies with big administrative data, and Susan kind of was running this lab at Stanford, kind of was also involved in running particular kind of targeted small experiments. And at that time, I was also talking a lot to people at some of the tech companies, kind of looking at doing experiments, but also exploring the benefits kind of some of the big observational data sets they had. And so here, we're going to look at 2 relatively narrow, kind of relatively specific settings, but part of this is kind of just thinking more generally about how we can systematically combine these things. So part of the vision I have there is to kind of think of this as you're trying to answer lots of different questions. You're not going to be able to answer them all by doing experiments. Experiments are always going to be small, kind of targeted and expensive, so you can only do a limited number of them. But if you have kind of big, complex models that can answer lots of questions, it's very helpful to make sure that they're anchored in reality, kind of having these experiments, having these targeted experiments to kind of pin down particular parts of the models where you're very unsure about the values of particular parameters can be very helpful to make sure that other inferences about questions that you can't answer directly with the experiments can be answered in a more credible way. And so here, this is kind of partly just showing that in some cases this can actually be very effective and can be very helpful, and we can get the benefits of both the observational data as well as the benefits of the experimental data by combining these okay. So kind of here starting sort of at a general level, I'm going to think of these of settings where we have these observational data that are often very large, so they give us a lot of precision for the questions that they can answer. They're often representative, often they come from administrative data, from databases that are comprehensive, that have the whole population, and so they're great in terms of external validity. But the analysis based solely on these observational data may suffer from lack of internal validity. We don't necessarily trust the answers we get just from the experimental data, from the observational data. At the same time, experimental data are often great in terms of internal validity. They give you very credible answers to the questions that they were designed for, but often they're for very unrepresentative samples. They're very small, so they don't give you a lot of precision. They don't have a lot of detail about things where you would actually like to have more detail about, and so they're not very good in terms of the external validity. And part of that's kind of almost built in when the Food and Drug Administration regulates the way experiments are conducted for new drugs. They insist on random assignment for these, in most cases, for these studies, but they don't insist on the study populations being representative of the target population. And they can't really do that because one of the conditions is that the participants need to give consent to the experiment, and the people who consent to do so cannot be guaranteed to be representative of the population of interest. So you can't really guarantee that you have both external validity and internal validity. So there's always going to be some concerns with experimental data. So what we want to do here is kind of figure out, we're going to look at methods for systematically combining experimental and observational data, kind of with two goals in mind. One is to answer questions that neither of these data sets can answer on their own, and a second to improve the answers to questions that we could answer with one of these data sets, but we may be able to answer that better in a more robust way by combining these data. And so if the longer goal is then to have methods that will make the experiments more valuable by allowing them to be used for questions beyond the ones that they were directly used for. And kind of what you see at the moment a lot in the experimentation in the tech companies is that they just only use the experiments for one particular question, and then essentially they throw the data away, but they just put them aside and don't really go back to them systematically. But here, in principle, we're trying to make these data from these experiments more useful. And second, that we make the analysis based on observational data more credible by grounding them, kind of by forcing them to be consistent with the experimental results. And to look at two specific examples there. One where we have two data, in both cases we have two data sets, an observational sample and an experimental sample. In the first case, the observational sample has all the relevant variables. So, and the application there we're going to look at is a study of the effect of class size on educational outcomes, on test scores at various stages in people's educational careers. And we also have the experimental data, but the experimental data don't have information on the primary outcome of interest, because it would take too long to do the experiment. So we made, clearly, if we look at the effect of class size, we're not really interested in what that does for test scores. We want to see what it does eventually in the labor market. That's the thing we actually care about. And we're just using these educational outcomes, these test scores, to see if there's any effect of these class size, these changes in class size. But we're interested in longer term outcomes. And so the second setting is slightly different. There, for the observational data, we're again interested in the effect of some intervention on long-term outcomes. The experiment only has information on the assignment and the early outcomes, but now the observational data has only information on the early outcomes and the long-term outcomes, but not on the intervention itself. And that's kind of something studied in what is called the surrogacy literature, and we'll see how some of these ideas from the first setting kind of change in the second case. But kind of to preview the results. So here's some data from two from one observational study, one experimental study on class size. The experiment is Project STAR in Tennessee, where they randomly assigned kids to small or large classes. So the treatment here is a small class. We're looking here at, so the labels is slightly mislabeled. So the first column with numbers is third grade, the test scores, and then 8th grade, and then 3rd grade in New York, 8th grade in New York. So what we see here from the experiment is that average test scores in 3rd grade are higher for the treated kids than for the kids in the small classes than for the kids in the regular size classes. Not surprisingly, you would think that having small class size is good, and the experiment shows that it actually is working. The test scores go up in 3rd grade. So difference is statistically significant. It's all great, and we trust that number. Then if you look in but what we would really like to know is what that effect would be in 8th grade. But we didn't see that in Tennessee, because doing that, knowing that number would have taken 5 years, 6 years to actually do it. And they didn't do the experiment long enough to measure the outcome for 8th grade test scores. But we had this observational data from New York, where we know class size as well, and we measure test scores both in 3rd grade and in 8th grade. And so what we see there is that in 8th grade, the test scores for the kids who were in small classes early on, so they were in small classes in 2nd grade and 1st grade, so they were in small classes early on, their 8th grade test scores actually lower than the 8th grade test scores for the kids in big classes, 0.037 versus 0.155, because that's a very big sample. We estimate that the treatment effect of being in a small class very early on, estimated on these observational data, is negative, and it's very precisely estimated. Now, do we believe that? Well, if we look in New York for 3rd grade, so again, this is the 3rd grade column for Project STAR, this is the 8th grade for Project STAR, this is 3rd grade for New York, and 8th grade for New York. So in 8th grade, we see this negative effect. But do we trust this? Well, if you look at 3rd grade, you see a negative effect there as well. So if we believe the 0.201 number for Tennessee for Project STAR, which I would argue we should believe because we did have a randomized experiment there, then the question is whether we should really believe these numbers here. There's sort of 2 reasons why these numbers could be different from what we see, why this number could be different from what we see here. It could be just that these kids in New York are just very different from the kids in Tennessee, that there's no external validity for the Tennessee study relative to New York. Or it could be that the selection in New York, that the kids in these small schools are different from the kids in the big schools. Now here we're going to double down on the interpretation that this is coming from selection. And so we have some adjustments to make to hopefully deal with the external validity. We have some parental, some household controls. But in the end, we're going to argue that this number is different, this minus 0.138 is different from the 0.201, purely because there is selection in New York. And so what we're going to do is adjust the data in New York in such a way that we're going to replicate the 0.201 number for 3rd grade in New York, and we want to see what that does to the minus 0.118 number for 8th grade in New York, and we're going to focus on that adjusted number. Now, sort of what is underlying that at some level is that the key assumption there that we're going to rely on. I'm going to give a graphical version of that here. I'm going to give a more equation-based version of that later, but it's always good to have some graphs in these talks and papers. What we're going to essentially assume, and so the graph doesn't do complete justice to what we're assuming here, but we're going to rely on the fact that whatever the unobserved confounder is that invalidates, that compromises the comparison for 8th grade, whatever that unobserved confounder is, it's the same thing that drives the difference for the 3rd grade test score. And so we're going to use the experimental data where we don't have an unobserved confounder that compromises the comparison for the 3rd grade test scores. We don't have an unobserved confounder that this classroom size was randomly assigned. We're going to use the comparison between observational data and the experimental data to extract the unobserved confounder and then use that extracted and constructed unobserved confounder and adjust for that in the 8th grade comparisons. And so, again, to kind of summarize what I've said so far, I'm claiming that I'm stating that the 8th grade result for the observational data, the minus 0.118, is not a credible estimate for the causal effect of class size on the 8th grade test scores, because we see that difference. In the 3rd grade scores. And so we're going to interpret that as the selection problem for the observational data. Now, how could we do that? So one thing would be just a very naive thing. We could say, well, we'll just subtract the difference we see for the 3rd grade test scores and subtract that from the 8th grade comparison and say, well, we're assuming the selection effect there is just additive and we can just take it out. Clearly that doesn't work in general if these primary and secondary outcomes are measured on a very different scale, if these are just completely, if these are different variables. It's also not clear what you would do if you had multiple secondary outcomes. So here what we're going to do is have a systematic way of adjusting for the selection that we see in the 3rd grade test scores. So I'm going to come back in a minute to how we actually do that, but once we do that, we get these adjusted numbers. So the raw differences, well, these are still somewhat covariant adjusted, but so now here the labels are correct. Before we had the minus 0.38, the adjustment gives us the exact same number as in Project Star by construction. That's what the adjustment is going to do. We apply that same adjustment to the 8th grade data, and now we get an estimate that is positive, that's 0.057. And so, my prior was that the effect of having a small class should be positive even on 8th grade test scores, and now we get an estimate. And so this is all great. Of course, the question is, does this actually really work? So now, at this point, the only basis for saying this is working is that I like this number better than the number I had before. But how do we know this is actually working? Well, I lied earlier, and we actually do have the number from Tennessee for 8th grade test scores. So we do actually have the experimental data there that includes 8th grade test scores. And so we know that the experimental number there is 0.085. And so now the comparison is whether the proof is that the adjusted number, the 0.057, is in fact quite close to the 0.085, despite the fact that in calculating this number, we never used any of the data from Tennessee beyond 3rd grade. We only used the evidence up to 3rd grade, applied that adjustment, and that turned out to adjust the New York estimates in a substantial way to very close to the Tennessee number. In fact, actually, let me see. Oh. So now there's actually a slide. There's a slide missing, and I don't know what happened. I must have sent the not included. So yeah, so which is a shame because that slide shows this for a number of different grades, and you see that sort of every time you adjust for the third grade scores, that removes the difference between the observational study comparison in that particular grade and the experimental estimates. So it doesn't, we didn't just take A grade scores because it worked there. It works kind of for the whole range of grades. But so now let me go into some detail here on how we're actually doing this. So the specific setup is one where we have these two samples, one denoted by PS for Project Star, one by NY for New York. In the Project Star sample, we see the treatment, we see the third grade test scores, and we may see some other covariates, some other fixed characteristics of these individuals. For New York, we see all the variables. We also see the outcome of primary interest, in this case, the grade test scores. So we think of their, maybe we're interested in causal effects, so we think of there being two potential outcomes for each of the outcomes, and what we're interested in is estimating the average effect of being in a small versus a big classroom in New York. We can also focus on the average effect in the experimental study. That doesn't really change the basic complication that comes from the fact that we don't actually see the experimental, the primary outcome in the experimental data. So, what assumptions are we going to make? First, essentially definitional, that we think the observational study has internal validity. That's the population of interest. Second is that the experimental sample has internal validity. And so I'm formulating that here is that the treatment is independent of the potential outcomes for 8th and third grade test scores in the Project Star sample. And so here, that's again not a controversial assumption. That's just satisfied by design. We can weaken this. We can just assume that it's unconfounded, conditional on a set of covariates, so we don't formally need experimental data, but we're going to rely on the fact that we're willing to assume that in one of these data sets we do have internal validity. Now, we could assume that in the observational data we have unconfoundedness, that we have enough covariates that adjusting for those covariates means that the treatment is unrelated to the potential outcomes. Then we would be done, and we would need the experimental data. We could just rely only on the observational data, because that is, at some level, that's a perfectly reasonable way to go. That's probably what we do if we didn't have the experimental data. But at that point, there's not really any role for the experimental data. You could also, there's a paper by Nathan Kellis now that combines the sample and says we have unconfoundedness in the combined sample. That's kind of a little, that's a little bit more difficult to interpret, kind of why separately in each of the samples you wouldn't have unconfoundedness, but you would have it in the combined sample. But they study a setting where neither of the samples is experimental. So it makes a little bit more sense, but it's not really an attractive assumption in this setting. Third assumption is that we assume that after adjusting for some of the covariates, or unconditionally, we could weaken this to adjusting for covariates, the two samples are comparable. And so this is saying that fundamentally the New York and Tennessee samples are not different, conditional on some characteristics. That's of course a big assumption here, but that's really important here. We are interpreting the difference between the minus 0.138, what we get in New York, and the 0.201, what we get in Tennessee. we're interpreting that as the effect of selection rather than as the effect of differences in these populations. And so you need to somehow attribute these differences that you see to partly selection and partly the external validity problems. And there's nothing in the data that's going to tell us that it's one thing rather than the other. But so here we're assuming that it's all coming from the selection. Again, we can condition on covariance. That's fine, and that's what we do in practice. But we need something like this. But this in itself is still not enough to get us to point identification of the treatment effect. And so we don't want to assume complete unconfoundedness, but and in combination with the external validity, that would actually give us some testable restriction, but then we wouldn't need the experimental data. And so what we assume, and that this is sort of part of the assumption that's actually difficult to capture in the graph, we're assuming that if we knew the third grade outcome for a particular sort of in small classes, then the assignment to treatment would be unrelated to the 8th grade outcome given small classes. And so this is very much like an unconfoundedness assumption, but the only problem that we don't see the third grade the outcome in small classes for everybody. We only see that for people who are actually in small classes. And so we can still estimate the conditional mean of 8th grade outcomes in small classes given all these right-hand side variables, but that's not enough because we can't undo the selection if we don't see what the marginal distribution is of 3rd grade small class outcomes. So even though assumption 5 looks very much like a regular unconfoundedness assumption, the fact that we only see this variable that we need to condition on if you're in a small class, or we only see it if you're in a big class for a regular class for 3rd grade outcomes in regular classes, means we can't use this directly. But this is where the experimental data are going to come in, because they allow us to figure out what that marginal distribution of 3rd grade outcomes given small classes is. And so we see one distribution of 3rd grade outcomes in small classes in New York, but we know that that's not quite the right distribution, but we can figure out what the right distribution is, and then we can reweight things, we can undo the selection there. And that's the point where we use the experimental data to undo the selection that we see in New York. So again, we can't use that assumption on its own. Even though we can estimate this conditional mean, we can't average that over the marginal distribution of y0, because we only see y0 conditional on w is 0, and it's no longer the same. But we can get that from the experimental sample and then undo And so the key identification result is that under these three, the first three assumptions, the first two which were not controversial, because the first one was definitional, second one was coming from the random assignment, the third one about the external validity, that is a strong assumption, and there's lots of cases where that would not be satisfied. But then the key thing is this latent unconfoundedness that is just a way of formalizing the idea that whatever drives the bias in the 3rd grade outcomes in New York is the same as what drives the bias in the 8th grade outcomes. The fact that the unobserved confound is the same for both these outcomes, that combination allows us to identify the average effect in New York. And so here, kind of to put that in perspective, going back to so actually, let me just go back so given this setup, there's only one variable that is missing, that's the primary outcome for the experimental data. You could take a little and Rubin type missing at random approach, where you assume that conditional on all the variables we see all the time, namely the treatment, the third grade outcome, and any pre-treatment variable, this outcome is missing at random. That turns out to essentially correspond to that is implied by the same the set of assumptions I articulated before. So that set of assumptions implies that you can view the 8th grade test scores as missing at random in the experimental data set. Now, given that, how can you actually implement that? There's sort of 3 ways of getting efficient estimators for that. And they're kind of helpful for thinking about, for understanding what's going on. One is a control function approach, where you essentially try to estimate that unobserved confounder. How do we do that? We look at the conditional distribution function of the 3rd grade outcome given within the treatment groups, and for the Project STAR example, that gives us a function, and we know that the marginal distribution of that is a uniform distribution just by construction. But now we can calculate the value of that control variable in the observational sample, and that captures the unobserved confounder. And so one reason why it's useful to think about that this approach is it shows you that now if we have more the secondary variables, more of these conditioning variables, we can create a higher dimensional control variable. And so we can deal with multiple unobserved confounders. We can deal with that with as many as we have secondary variables. So the more of these secondary variables we have, the more flexible we can be in the selection model that drives the selection into big and small classes in a way that allows us to control in a more credible way in our estimates for 8th grade test scores. So the latent unconfoundedness assumption implies that if we calculate the control variable and then adjust for that, the control variable we can now calculate for every individual in New York, we can use that as a control in an unconfoundedness type analysis, and the latent unconfoundedness implies that captures all the violations of the unconfoundedness, and so we can do an analysis where we rely on the assumption that conditional on that control variable assignment to the small and big classes is independent of the potential outcomes in New York, given that control variable and given any other covariates, any other pre-treatment variables we may have. Second, the strategy is just to directly exploit the missing at random connection. And so we could estimate a flexible model for the relationship between 8th grade scores and all the other variables, and then use that to impute the 8th grade test scores in the Project STAR sample, and then proceed, given that, and estimate the average effect there. The third strategy there is weighting the observations. In the end, we're always going to rely on the observational data to estimate the effect of being in a small and big classroom on 8th grade scores. And just we think that the small and big class samples are not comparable, and so we're going to need to reweight them to make them comparable. And we use the experimental sample to construct these weights so that the small and big classes are comparable in such a way that we replicate the 3rd grade results for the experimental data and have these weights be as close to constant as possible, and that turns out to correspond to the same estimators as before, and so that's going to give you another way of efficiently estimating the average effect of a small classroom on 8th grade test scores in New York. All right, so that's kind of the first part. I'm going to then talk a little bit about the second part, the surrogacy part. And so there, this kind of, so the key difference is that now I'm going to look at a case where the treatment is also not observed in the observational data. So it's a slightly different configuration of the data. And so this literature has a longer tradition in the biomedical settings where when you do drug trials, say in settings so for cancer drugs, often you can't measure the outcome you're interested in, say mortality, in an experimental setting fast enough. It would take many years kind of for the effects to show up there. So they look at intermediate outcomes, at surrogates for these primary outcomes. And so here we're going to take that a little further because we actually directly use the data that links the primary and secondary outcomes. Typically in the biomedical setting, we just take that as given and only look at the experimental evidence for the effect of the treatment on the secondary outcome. But so, compared to the previous setting, we now have an additional question mark in this sample, in the observational sample, where we don't see the treatment. And examples, so the motivating examples, kind of one is where I study was coming from. Suppose you have a job training program, we're interested in the effect of long-term employment, but we may not want to run the experiment for very long. So we see a bunch of outcomes early on. In the tech company settings, also you often run these experiments fairly short term. You want to make decisions quickly, but really what you're interested in is the effect on long-term engagement with the website or long-term expenditures or whatever the outcome is of interest there. So here, the application we're looking at is a data set where again we can validate some of these methods. This is a labor market program that was implemented in California in the 1980s called the GAIN program, the Greater Avenues for Independence. And because this is primarily linked to administrative data, it was actually later possible to do a very long-term follow-up, so we know what the outcomes were for these people for 9 years after their original program. So there were 4 sites where they implemented this program. We're looking here at the data from Riverside. So most of the time I do theoretical econometrics, but this is actually one time I actually visited this site in Riverside. At the time I was actually first started working with these data with Joe Hodson. I was at UCL. So Riverside is not that far from there, so we drove over there. And it was a very interesting experience. The most memorable part of that was afterwards we spent the afternoon there and people were hungry. So we went to this drive-through McDonald's or whatever the place was, but I'd never actually been there before, so I hadn't quite understood how the system worked there. So I missed the point where you order the food. And so I got to the point when you get the food, and someone had a bag ready and shoved it in the window, and I paid for it. So I got whatever the person behind me was ordering. And presumably the orders were screwed up for the rest of the day. So I learned my lesson not to go to these drive-through restaurants. But anyway, the Riverside program was a very special one because they were incredibly successful in getting people into jobs very quickly. Some of the other programs focused a lot on classroom training. In Riverside, they focused a lot on getting people into jobs very quickly. But in the longer run, they didn't necessarily have quite that good an effect on employment. And so here we're going to look at the setting where we have these two data sets. In the experimental setting, we don't know anything about the long-term outcome, but we have experiments, so we're very sure we can get the effect of the treatment on the surrogate. And now we're essentially assuming that we can estimate the causal effect of the surrogate on the outcome in the observational data, so that there is no unobserved confounder there between the surrogate and the outcome in that setting. So you can think of this from a mediation perspective as that there's the entire effect of the treatment on the outcome goes through the surrogate. And so again, it may be very helpful to have multiple surrogates. And kind of one of the challenges in the tech company versions of this is if they're looking at long-term engagement, but they're measuring the effect of the treatment through whether people click on things, click on ads or advertisements, for example. The concern is often that creates incentives for having clickbait, where you make the advertisements very interesting but not very effective in actually converting the clicks into whatever outcome it is that you're interested in. So from that perspective, it's very helpful to have multiple surrogates. You have surrogates that span the entire range of mechanisms through which the treatment affects the outcome. Now here, I don't have the slide with the kind of full set of results. So here we took the data from the experiment. We split the data from the experiment into two parts. One we go to where we threw away the treatment assignment and just looked at the outcomes, the employment records for these individuals over those 36 quarters plus a bunch of pre-treatment variables. And one where we just looked at the indicator for whether the people were in the training program or not, and outcomes up to the first T quarters. And the question was, if we only use outcomes up to the first capital T quarters, how well do we do in terms of predicting the average effect of the treatment over that 9-year period? So the average effect was about so there's this solid line that's about 6 percentage points increase in employment. And so what you see is, if you just take the naive estimate, if you take the average employment up to quarter T, and say, well, that's a good estimate of what the average effect would be over a 9-year period, you see that initially you way overestimate that, and it takes a long time before that actually gets to the average. Using the first T quarters as surrogates, we see that after about 6 or 8 quarters, we actually get a pretty good estimate of what the overall effect is. So we don't necessarily need to run the experiment for 9 years to see the effect, what the effect is over that longer period. And we see it after about 2 years or so. We would be fairly confident. Kind of looking at this for different outcomes. So here we're looking at the 9-year outcome, but you see this actually holds for all intermediate outcomes as well. So again, we can get the average effect for any horizon, basically using 6 quarters of post treatment outcomes as surrogates. Changing the number of quarters we use as surrogates, you see that kind of using 1 or 2 quarters is not enough. You clearly need about 6 quarters, but after that, your estimates don't really change very much. So it's all suggestive of the fact that having about 6 quarters of data after the experiment is enough to predict what the long-term effect of the treatment is going to be. So what are the assumptions here that we need for this? One is that the assignment to treatment is essentially is ignorable. We have unconfounded assignment, but the key assumption is one version of this is called the Prentice criterion. We need that the primary outcome is independent of the treatment, conditional on the surrogate and whatever pre-treatment variables you have. And we need some comparability of the samples. We need some version of external validity where the experimental and observational study reflect similar populations. And so the key thing is really the surrogate assumption. I want to give different versions of this, but essentially it's all coming down to some version of saying that whatever the mechanism is through which the treatment affects the outcome, it goes through that set of surrogates. It flows somewhere through at least one component of these surrogates. So there may be different mechanisms, but you need to find a set of surrogates that contains all possible paths from the treatment to the outcome to get the overall effect on of the treatment on the surrogates. Now, in the paper, I'm not going to go into detail here, but in the paper we spent a lot of time thinking about what happens if that's not true, because of course in practice it's unlikely that that's true. Where this is in the end still useful, at least from our perspective, and the way this is used at a lot of the technologies, irrespective of whether this holds, this gives you a systematic way of balancing a bunch of intermediate outcomes. So in many of these experiments, there's a whole bunch of early measures that you can use to evaluate the experiment. So in a case of in an online shopping setting, you could look at how much people spend on the website. You could also look at how many times people come back, or you can look at how many items they actually bought, or how much time they spend on the website. And all of these are sort of indicative of people being engaged with the website. But if what you care about is sort of how much they spend over a 2-year period, then it's not immediately clear how you should balance these different intermediate variables. Suppose you see that there's no significant effect on how much people spend early on, but actually bought more items, or they spend longer on the website, or they looked at more, they came back to the website more often. Is it a good thing or a bad thing? And what this is telling you is that really the way you should balance these different things, the way you should trade off these different things, is by looking at how well they predict the primary outcome. So if you have these two variables that are measured on a very different scale, all that matters is how well they predict the outcome, and that tells you how to weight these different secondary outcomes. So, but an alternative way of thinking about it, and this relates to the mediation literature, is if you think about there being causal effects both of the intermediate outcome and the treatment, then essentially the key assumption is saying that there's no direct effect of the treatment given other than the effect that passes through the surrogates. And so kind of from a mediation perspective, if you think about there possibly being an error from the treatment to the surrogates and one from the surrogates to the outcome, there cannot be a direct effect of the treatment on the final outcome. And so this set of assumptions then applies the same, the Prentice criterion, the version of the surrogacy assumption. Now, to actually implement this here, things get a little messier. There's now a whole bunch of ways you could try to estimate this So in principle, there's a propensity score floating around that tells you what the probability is of being treated as a function of the covariance. And so that if we have experimental data, that would actually be flat. We would know that. But in general, that could be a function of x as well. Then we have what we call the surrogate index that measures the relationship between the primary outcome y and the intermediate outcomes and the covariance in the observational sample. And finally, we have the surrogate score that gives you the probability of being in the treatment group given the value of the surrogates in the experimental sample. So that's kind of a funny thing, because now we're looking at the probability of being in the treatment group given an outcome variable. Where typically you would look at the relationship between outcome variables given the treatment. Then finally there's what we call the sampling score that measures the relationship between the two different samples, the experimental sample and the observational sample. We're going to ignore that for the moment. But then, just like in the first setting that I discussed, there's sort of three ways of estimating the average effect. You can do it through estimating the surrogate index and just reweighting that in the experimental sample. So you would estimate the surrogate index, you would estimate the relationship between the primary outcome and the surrogates in the observational sample, and then just use that in the experimental sample as the outcome. You could use the observational sample, but reweight things using the surrogate score, and you could use a combination of these two in a double robust influence function based approach. And like in the previous case, all three of these are going to give you efficient estimators for the average effect. And so, kind of final comment, so in the case where you're actually willing to make the assumption that the surrogate index is linear in the covariance, then it kind of becomes very clear that what you're doing is you're looking for a way of balancing these different outcomes and for a way of putting weight on these different outcomes proportional to how they affect the primary outcome. And that's kind of related to what Perrin and Kenny do in the mediation literature. I mentioned kind of you can figure out what the bias comes from violations of these assumptions and when this is going to do well, but let me skip that and just make a couple of concluding comments. So what we're interested in here is trying to find systematic ways of combining experimental and observational data. Both of them have their strengths and weaknesses, but combining them allows us to address some of these weaknesses and benefit and combine their strengths. These are just two examples of doing that. Kind of, again, much more expansive vision of trying to build these bigger models where you use the experimental data to make sure that these models are credible in the past, where they're most tentative in the theoretical parts. And in both these cases, in these examples at least that work well, there are sort of clear ways that these estimates were more credible than those based on one of these samples alone.
Wonderful. We've got a bit of time for some questions if people have got things to ask. Often when we, just to get things going, we often think about observational data as adding the ability to do more counterfactuals. The experiments are limited, they're very successful at looking at a limited thing. And here you're kind of going partly that direction, but not fully. In the sense that there's a kind of dynamic here, there's a kind of counterfactual out there. The way I see it, a kind of longer run counterfactual. You've got some information on a short run counterfactual that you've run for experimentally, and then you want to somehow say something about the longer term here. And is that, and so what you've got is a set of assumptions that allow that to work through a kind of surrogacy assumption. That you know the mechanism, or you know the majority of the mechanism through which that longer counterfactual works, for example, in the outcome there. I guess that's, in a way, a question is, do you think you can take this further? There's a kind of dynamic causality here, and you're missing one bit of the link, so you've got this, this idea. Often we're thinking of counterfactuals that are not necessarily in that dynamic way, they're just an alternative. But I imagine you could think of a set of conditions by which you can learn about that other counterfactual through a set of surrogates. So just as a point to get the question going.
I think when you start saying, well, experiments give you very good answers for very limited questions, I think that's key here. And sort of what I've seen in many cases is that people focus too much on using these experiments to just answer those limited questions, rather than actually think about what would actually be, given the whole range of questions we have, what would be the most useful experiments to do? What are the things we're actually most unsure about, whether it would be the biggest benefit from learning more? And that may not be, that may not lead to an experiment that's going to give you directly some decision to make, but it's going to make all the subsequent decisions better informed than they were before. You can think about that. You may look at lots of things that change various aspects of the exchanges on these various online platforms, say Uber or Lyft or Airbnb. But one of the things that drives almost all these decisions are what are the demand elasticities. So trying to figure out directly what are experiments that tell us a lot about demand elasticities is going to help us learn about a huge range of counterfactuals, rather than just what happens if on Airbnb we give this, we change things a little bit this way. In the end, it's always going to come down to understanding how elastic demand is, and how consumers are going to react to different incentives there.
So I get going. So in a way, you can turn it on its head and talk about how to design the best experiment given the thing you're trying to do. And in a sense, that's what the surrogate is saying. You have a set.
That's part of the bigger project. And there's a lot of very interesting work going on that I kind of both in some of these companies and in their world on how to do better experiments compared to what Fisher and Neyman were doing when they were doing these agricultural experiments. We fertilizer A here, fertilizer B there, and then you sit back and wait till the end of the season to see where the corn is growing. Now, in many of these settings, you get a very quick feedback, so you can do much better in terms of adaptive experimentation, but of course you need to keep track of the fact that it's the long-term outcomes you're actually interested in. Often these experiments are in settings where there's multiple populations interacting, because these are marketplaces like Uber or Lyft, and so you need to figure out how both sides of the market are responding and how the new equilibrium gets formed. So the experimental environments are much more complex, and so thinking about how to do optimal experimentation is a much more interesting question there, where kind of before it's sort of fairly obvious that if you put 50% in the treatment group, 50% in the control group, that's pretty close to optimal. But in these settings where there's spillovers and interactions between different populations, it's going to require a lot more theory to think about what good experiments is, because you need to think about the nature of these interactions. And of course, these platforms create very particular structures of these interactions. If I get a ride on Uber now, that affects everybody else in the market, because I take one particular driver off the market for as long as my ride lasts. But it's a very limited, it's a very specific way my spillover affects everybody else. It affects everybody else in the same, well, not quite in the same way, because it depends on where you are, whether that rider would be a possible alternative for you. But it means that these experimental design questions become much more complex, but that also means we're going to rely much more on combining the experiments with observational data, because the experiments are never going to be powered well enough to tell us the answers to the questions we're going to be interested in. So you need to leverage a huge amount of observational data people have available in these settings.
That's great. Let's open it up a bit. Andrew, front here.
So to get to grips with these results, I guess you have to believe some of these restrictions are true. But I was wondering whether, in fact, once you have multiple surrogates, under the restrictions you've imposed, you could throw some of them away and expect to get similar but not necessarily such accurate answers. So is there then the possibility of detecting failure of these restrictions once you get to that position?
Well, so in principle, there's sort of a weakest version of these assumptions in the surrogate case, where there's no testable restrictions left. Yeah. So these are just identified. So if I say, actually, I need all these surrogates to make this work, there's multiple paths from the treatment to the outcome, and I need one surrogate for each of these paths. There's nothing testable, and that in some sense it's nice to have that missing at random connection. So I didn't actually highlight that for the surrogate case, but there's a connection like that in that case as well. So there's nothing testable about it, because that doesn't make the assumptions more plausible. And again, in practice, because we don't think these things really hold exactly, they're at best some approximation. But so the way I've argued, when in settings where we're actually making decisions based on this type of thing, we see, let's kind of think about a case where we have two surrogates, and so we do an experiment. We see there's a positive effect on one variable, there's a negative effect on another variable. How do you make a decision then whether to implement the thing? I suppose that both are estimated very precisely. What I've seen in some of these discussions is that if some of them are not significant, people say, "Well, okay, we ignore these because these effects are not significant." And so that makes it easy. Now there's only a couple left. I suppose there's still two left. One of them is positive, one of them is negative. Then people start arguing, and there's a guy who used to be who used to run the experimentation at Microsoft. He said, "Well, then the answer is it's the highest paid person's opinion and this gives you one way of systematically balancing these outcomes that may be measured on a completely different scale. It says measure, take away the average of these two in the linear case, weighted by their effect, by how predictive they are of the final outcome. And so if you say, well, I don't believe the surrogacy assumptions, then essentially you're saying, well, I have a better way of constructing these weights, because there's nothing in the data that's going to tell you that these weights are better. And, it's fine if you want to say, I don't believe this assumption, but this gives you a starting point to think about how to balance these different outcomes that may be qualitatively very different, and may have very different interpretations, but now at least there's some data-driven way of informing that decision.
Yeah. Other questions? I can see one here from Kirill.
I have a question on the first setting.
Yeah.
So, the way you treat the relationship between the 8th grade and the 3rd grade reminded me a bit of kind of lag-dependent variable structures. And I was wondering if there is a version of that which instead would rely on something like fixed effects. Whether, there is some changes in changes type of approach to learn about how the distributions of the third grade and eighth grade grades differ, and then you apply kind of that transformation to the experimental data, if that would be like another way of approaching the problem.
Yeah, that's an interesting question. So I've not thought about it that way. And so when I thought about kind of these nonlinear difference in differences settings, I was thought about sort of a two-period case. I couldn't quite figure out how to make them work in multiple periods. And the interesting thing here is that it's very easy to accommodate multiple secondary outcomes, because you get a control variable for each setting. So that would be an interesting thing to explore. So from your question, I do think that yes, there is some connection, but I've not thought about that. So I don't know specifically whether how you can transform one and the other. So think about it more.
Other questions? Well, yeah, there's one there.
So my first question is, when you mentioned that the test scores are not comparable for third grade and eighth grade, and when you want to use the observational data rather than experimental data, there could be like for different areas in different states, the students have different standards of tests that are not comparable. But then how would you deal with such issue?
Yeah, so here we're assuming that the outcomes are comparable, so they are measuring the same thing. We're allowing for some variation in the populations by controlling for fixed characteristics of the household. So we know something about socioeconomic status, that if there are some individual characteristics for these kids. But we do rely, listen, clearly this would be easier if the observational data was from the same region as the experimental data. The further you move away from that, the more controversial some of these assumptions are. But in some sense, the fact that even despite New York and Tennessee being very different, we still managed to replicate the experimental results in Tennessee using the observational data in New York suggests that the populations were not so dramatically different that in the end they were comparable enough that we can combine them in a useful way.
Do you think it's useful to kind of compare the ordering, like the quantile the students within that state, or kind of find like a standard you can compare nationally?
Yes, so the test scores themselves, it's a similar test, and so they're normalized, so they standardized to essentially comparing the normal contrast from the normal distribution. That clearly helps. Then, because the design at the moment we just look at average effects, so you can also look at other aspects of the distribution. So you could look at quantiles as well. And we do that at some point, and we get similar results. The adjustment works to make the Tennessee and New York data comparable.
My second question is, would you want to extend the external validity of the average treatment effect by combining the experimental data and observational data? Do you think that's also applicable to local treatment, local average treatment effects when you, for example, get from like regression discontinuity, things like that? Do you think that's has the potential to extend the external validity?
Yeah, I mean, that's sort of somewhat application specific. With regression discontinuity, it's sort of very clear that you get effects that are local, that in principle are valid only for subpopulations, but it doesn't mean that the effects couldn't be valid for other parts of the distribution. And there's kind of a lot of work showing that you can look at the distribution and kind of see, in a sense, of how the different subpopulations are comparable. So there's what you can do there to build a stronger case for external validity. But whether that works, it depends a lot on the particular context, but it's certainly worth exploring further.
Does anyone else want to ask a question? Maybe we're too quiet. I can see one there.
Thank you. I work on macroeconomic policy, and policymakers are, as you said, keen to commission experiments. Just in terms of advice, would you say commission a kind of short experiment, learn from it, then expand, or do you think it does need a multi-year study that combines the short-run experiment with a much longer research period? And how would you advise policymakers? Should they adapt then to early feedback and adapt the policy if early results come through from a short-run experiment? Thanks.
Yeah, that's a very interesting question. It depends a lot on the sophistication of the decision makers. Of course, a huge tendency to look at results of experiments, and I alluded to that kind of before with the surrogates. So that if you see facts that are not statistically significant, to interpret them as there not being any effects. And so so in principle, I would like to look at early results and adapt the experimental design kind of as you go along, and that would be a much more effective way of doing things. But you do need the decision makers do need to have the sophistication to understand that some of the results that are not significant may be there, and they should not be interpreted as the absence of results. So you see that a lot and that's sort of a big danger of doing underpowered experiments, like they may then stop the ability to further explore the particular pathways. But in principle, the ideal thing would be to see the experimentation as sort of a process where you continually learning from what you see and adapting and moving towards more effective procedures. But that can be a tricky thing in practice if people are very focused on short-run things.
Great, thank you. Anything else? I think it's probably time just to thank Guido for this fantastic talk.